Hi, welcome to your lesson on derivatives of natural logarithmic functions and exponential functions with the base e. Exciting topic. Let's get going. First of all, let's remind ourselves what a derivative is. My favorite graphic here. A derivative is basically just the tangent line or the equation of the tangent line to a curve. So we have a blue curve here, and we can see we're trying to create a tangent line. That dotted orange line is a perfect tangent line. So that's all a derivative is. Just a tangent line to a curve at any point on the curve. So looking at that, what is a derivative? Here's another look at that. We have a curve, this quadratic in blue, x squared. And then if we say, what is the slope? Because slope is represented by the tangent line. So what is the slope at every point on this graph? Well, let's take a look. First here, the slope is a pretty big negative slope right here. If you drew a tangent line here, it would be a big negative number. All right, and then here will be a lesser negative number and even a lesser negative number. And you can see the green line, which is the derivative of this function, has negative values down here, negative y values, right? So that's representing the negative slopes. When you get to the bottom here, there is no slope at all. And notice the green line at that point has a y value of 0, so it's saying no slope. And then the slope is now positive, and you can see the green line now has positive y values. And then the positive y values increase because the slope here, the positive slope, increases as well. So that's the basic idea of a derivative. I hope you remember that from before. Again, derivative is just the equation of a tangent line to a curve, or in other words, the slope. Okay, we learned some basic rules of derivatives. One of them was called the power rule. It looks like this. When we have a function like this, the derivative is this. You drop the 4 and then reduce this by 1. Derivative of this, drop the 5, reduce by 1. And then last one here, drop the 28, reduce by 1. That was called the power rule. It was our basic starter rule for derivatives. We're going to use that and some other rules now when looking at these graphs. But first, an investigation. We're going to fill this table with values, and we're going to use Desmos for this part, the derivative part of the table. But this first part of the table should be easy because we have these functions. There's all these different functions starting with 2 to the x, and you're putting 1 into that function for x. So what do you get when you put 1 in there? Well, I hope you're thinking, obviously it's 2. So what happens when you put a 1 into this function? 2.1. And so on, and so on, and so on. All those functions are very simple like that. You put a 1 in them and you just get the value of the base. In this case, the base is e, Euler's number, which means we get 2.718. And on all the way to 3. Okay, so now we're going to look at Desmos, and I think I just revealed this value, but there's the first one. Let's take a look at how we can get those values on Desmos. So now we're going to need the derivative of that, and we're going to figure out what happens when you put 1 into the derivative function, and that's our first value. So let's go to Desmos. I think I'm ready on Desmos. I have a curve set up here, exponential, a to the power x. So a is that base. And again, in our table, the base went from 2, 2.1, 2.2, and so on and so on. So I'm going to have that base go from, and you can set what this slider has, right? It has all kinds of values, but I set that. So let me show you how. Click on there, and you can set it. I want the base to be between 2 and 3. And here where it says step, I'm choosing the amount it will change by each time I move the slider. And I want it to change by 0.1 because I want it to go from 2 to 2.1 to 2.2 and so on and so on. Okay, so I enter that on Desmos. You're going to need that. So if you haven't gone to Desmos yet, get there now. And we're going to try to find out what the derivative values are, right? Because our goal in this table is to find out what's the derivative when we put what's the value of the derivative function we will put 1 into the derivative, right? So I'm going to type in the derivative here, f primed of x. And now, I'm going to put 1 because we're always putting 1 in there. And notice, see, for the first function with the base 2, it gives us 1.39 or 1.386, which is what we had here. Now I'm going to shift it and see what happens when I get 2.1 as the base. So you do that now and tell me what the next, let's say, tell me what the next 3 values here should be. Okay, so I'm shifting it now. 2.1, there's my number for the derivative when 1 goes in there. 2.2 and 2.3. All right, so I hope you saw those numbers and you got the same when you tried this experiment. We have that value, and on and on and on. We actually keep going down the list here. Here's all the values. But there's something interesting that happens somewhere in this table. What do you notice? Well, the thing to notice is certainly this, that when you get to the exponential function with base e, that the function's value when 1 is put into it is equal to the derivative's value when you put 1 into it. So that's interesting that the two functions, the original and the derivative, produce the same value when you put 1 in. So what does that tell you? We're going to look at the derivative of the function y equals e to the x, that function. So here we are, that initial function, and we're going to check what the derivative of it is. To do that, we're going to think back to what we just did. When we put a 1 in there, we got e to the 1, which is 2.718. But also, when we put a 1 into the derivative function, we also got 2.718. So what does that tell you about the derivative? Well, I hope you're thinking it's obvious. The derivative must be e to the x. It must be identical to the original, because if putting 1 into both functions produces the same number, that means both functions, the original and the derivative, must be the same. So here is a derivative of e to the x. This is very special, clearly, because there is no other function like it, where when you take the derivative, you get the same function. All right, no other functions are like that. Okay, so with that in mind, fill this table. If you had your e to the x function and your derivative function, and you put 1 through 5 in there for x, what would you get on each side here? Well, that should be clear. Like, we already put 1 in there for both, and we got 2.718. And then if you put 2, you get those two values, and 3, and so on. But these values are less important than the fact that they are the same. All right, again, because e to the x and its derivative are the same function. Very interesting. All right, now let's shift our thinking to natural logarithms. We just talked about exponential functions with base e. Now let's talk about log functions with base e. And remember, those are called natural logs, ln x. Okay, so for this second investigation, we're going to use Desmos. We're going to take a natural log function, and we're going to find the derivative of it. Our goal is to figure out what is the derivative of it by doing this table here. So our steps are to, let's see, let me go, yeah, we're going to go Desmos. I'm going to enter the ln x function. Let's see what it looks like. So clear this out. We're done with this part. F of x equals natural log of x. Okay, there's the natural log function. That looks about right. Okay, like a log function. Then we're going to put, I'm going to add a table. I press plus and then table, and in here I want to have x values, and here I want to have f of x1. Let's see. Okay, so when I put, oh no, I don't want f of x1, I want the derivative. I want to see what happens with the derivative. So I'm going to put a 1 in there, I get a derivative of that. Okay, I'm going to put a 2 into the derivative function, and it produces this. I'm going to put a 3 into the derivative function, it produces this. I'm going to put a 4 into the derivative function, it gives me this value. And then a 5, and that, and then we're going to put a 10 in there. Okay, so I've put all these values into the derivative, and it's produced these values. And you can see the ones it's produced here. And that makes sense in terms of the derivative, because again, here it's a big slope, and we can see a positive, big positive value. Here's less slope, but still positive, we can see a positive value. Less, basically the positive slope is decreasing as you follow the original function. So the positive slope values, which are the derivative function, are decreasing. Okay, but what do you notice here? There's something very interesting in the values here. When we put a 2 into the derivative, we get 0.5. When you put a 3 in the derivative, we get 0.333, and so on and so on. So let's take a look here. And there's, when we put a 2 in there, we got 0.5, right? When we put a which is actually a half, right? When we put a 3 in there, we got 0.33, which is actually 1/3. Notice all the other values here. So what do you notice? What does this tell you about the derivative of ln x? Well, I hope you see the clear indication there, and it shows you that the derivative must be 1 over x, because every time you put a value into the derivative, you get 1 over that value, right? When you put a 3 in, you end up getting 1 over 3. When you put a 2 in, you get 1 over 2. When you put in a 5, you get 0.2, which is 1 over 5. So, or 10, you get 1.1, which is 1 over 10. So that is the derivative of a natural log function. So let's recap. You just learned a derivative of a base e function, exponential function, is e to the x. And then you just saw now that when you have a ln x function, the derivative of that one is 1 over x. Memorize these two very important derivatives. We also know some other rules. These are not derivative rules, but they are rules that will help us. When you have a to the power log with the same base, see the base of the exponent and log is the same, that equals x. All right, when you have a log with base a of an exponential with a base a, the bases are the same again, equals x. Over here, we have e to the power ln x. That means we have an exponential with base e and then a log with base e. Again, same bases, therefore the answer is x to that, or the simplified form is x. And finally, a log base e exponential base e, same base, x again. Remember these, when you spot those, to always change them into their simpler form like this. Okay, let's do some problems. So you have these three here. Using what you just learned about derivatives, find the derivative of this first one. Well, that one is pretty basic. The derivative of e to the x is just e to the x, so the derivative of that is just 3 times itself. It just ends up being the same. Next one. Also pretty simple. We learned by the power rule that derivative of x squared is 2x. You drop the 2 down. And we just learned that derivative of ln x is 1 over x. So there's our derivative of this function. And c, in c, you could look at it like this. You could say, okay, this is a natural log, so I'm going to do 1 over this whole thing times itself. Why am I doing that? Because this is actually chain rule, and we'll talk about this a little bit more in a moment. There's a chain rule here, so I multiply by itself and then by the derivative of the exponent there. So this is kind of a complex way to look at it. When we look at chain rule in a minute, you can look back on this. But the easier approach, and by the way, these cancel and you're left with just 3. The easier approach, again, is to use this rule. When we see something like this, log base e, and this exponent has a base e also, it just becomes x. So in this case, ours can be rewritten right away as 3x, because this can be rewritten just as that exponent, 3x. And now the derivative of 3x is 3. Okay, next, try this one right here. For a, you should have this as your derivative. Check your work. Again, e to the x is just itself when you take the derivative, and ln x is 1 over x, therefore 2 times 1 over x is this. How about the second one? Well, second one, let's flash back to the chain rule. The chain rule tells us this. If we have a function like this, we know by power rule you drop the 4, 20, x cubed. But what happens when you have something like this? I have a function within a function. So over here, I have to do the power rule like we did here, where you drop the exponent. So I'm going to drop that exponent in front of this and have a 2 there. But also, since there's a function within there, I have to take the derivative of the function inside and multiply by that also. So let's take a look at that. So here we have this part is when I dropped it. Oh, I think there it is. I dropped the 2 down. There's this part that stays there. This became a 1 now, and we multiply by the derivative of the inside part by chain rule. And when you multiply this 2 through there, you get this, and then multiply by 6, take it a step further to that. Okay, that's chain rule. We're going to use it on this next one here. Try it. Okay, so you have this, and that becomes that. Why? Because the derivative of this is itself, but by chain rule, you have to then take the derivative of that little function, which is exponent, and the derivative of that is 2, so you multiply by that. Okay, next one. For the next one, you'll need to remind yourself of the product rule. There it is. I'm going to leave this screen very quickly, so write it down or remember it. And now try product rule here. Check your work for that one. Finally, D. In D, we need to remember the quotient rule. The quotient rule is even bigger than the product rule. There it is. Remind yourself of that. And now try the quotient rule in D. Check your work there. A little bit more complex now for sure, but you're using the basic ideas of derivatives of e to the x and ln x. I think I have a few more, so try these ones here, and remember the little rule about what this simplifies to and what this simplifies to. Now check your work for number 2. Remember those rules of derivatives. Check that carefully, what happened there. And then for number 4, we're going to use that rule to simplify this into 4x squared right away. Derivative of that is this. And number 6, we're going to use that rule to simplify this right away into this 4x. And then the derivative of that is this. Okay, so you're getting back into derivatives now. Hope it's going okay. Final problem, this one. This is going to be a challenge for you at this moment, I'm sure. Check your work. And I hope that reminds you how to deal with questions like that. We did a lot of those back when we did derivatives. Good luck. See you soon.